Okay, let's dive in. When you think about numbers, you probably just think, counting things, maybe balancing your budget. But the material we looked at starts with this really cool idea. Numbers aren't just tools. They're like the fundamental language of the universe, hiding right there in plain sight.
They really are. You see it encoded in nature, right? Like the perfect spirals in a sunflower, those follow specific number patterns. And then there are the equations, these elegant formulas describing everything from tiny particles to huge galaxies. And something maybe more relevant for you right now, your internet connection. It's secured by the weird properties of certain numbers.
Exactly. And that's what this deep dive is all about. Welcome. We're taking all the sources you sent, articles, notes, research, and we're pulling out the most important stuff, the key insights.
Yeah, our mission here is to sift through it all together, find those surprising facts, those moments that make you go, uh-huh, and really get you up to speed on the history, the nature, and even the really baffling unsolved mysteries surrounding numbers, from the everyday ones to the truly strange ones.
So we're going to look at the whole family tree of numbers, which gets kind of weird. We'll explore why 10 seems to rule the world mostly. We'll uncover secrets hidden in geometry, like in circles and spirals, with constants like pi and phi.
And we'll meet the number that pops up everywhere when things grow or decay. We'll even touch on numbers that seem totally impossible for centuries.
Right, and primes, the super important prime numbers, why they protect your online stuff. And then finish with some math puzzles that sound simple.
Yeah.
But nobody can solve them. It's wild.
It really is a whole universe just in numbers. Let's get started.
All right, so the sources kick off with this idea of the vast landscape of numbers. It does feel pretty huge at first.
It is immense. The universe mathematicians play in is vast. And the material points out maybe the first big split, the fundamental division, is between real numbers and imaginary numbers.
Okay, real numbers. Those sound, real, like the ones I use every day for counting, measuring, putting on a number line.
Exactly. The sources describe them just like that, all the numbers you normally meet. Positive, negative, zero, fractions, decimals that stop or repeat. They fill up that familiar number line. But then you have imaginary numbers. And the material notes, for centuries, these seem completely nonsensical. Some even called them heretical.
Heretical, wow. That's strong. What makes them seem so impossible?
Yeah.
So imaginary.
Well, it all boils down to the idea of taking the square root of a negative number, specifically the square root of -1. The sources use I for that. Mathematically, you just can't square any real number, positive or negative, and end up with a negative result. So square root of -1 seemed impossible.
Right, yeah. Because 2 times 2 is 4, and -2 times -2 is also 4. You never get -4 that way.
Exactly. But the sources kind of hint that even though they seem weird at first, these imaginary numbers, especially when you combine them with real numbers to make complex numbers, they turn out to be incredibly useful, like essential in engineering, quantum mechanics.
Okay, so real and imaginary make complex. Got it. But back to the real numbers for a sec. The sources break those down even more, which feels a bit more grounded.
That's right. Within the real numbers, you've got rational numbers. Basically, anything you can write as a simple fraction, a ratio of 2 whole numbers. So integers, whole numbers, natural numbers, decimals that end or repeat, they're all rational.
And the flip side is irrational numbers. Their decimals go on forever, never repeating, and you can't write them as a simple fraction. Pi is the famous one, right?
Pi is the classic example, yeah. And the sources share this amazing story about another irrational number, the square root of 2. This is a really key nugget. See, the ancient Greeks, especially Pythagoras and his followers, they believed the universe was fundamentally built on whole numbers and their simple ratios. Everything was orderly, rational.
And then someone figured out the diagonal of a simple square, one with sides of length 1.
Which turns out to be the square root of 2, a number that just didn't fit. It couldn't be written as a fraction. The sources say this discovery absolutely horrified the Greeks.
Horrified, because it messed with their whole perfect ordered universe idea.
Exactly. It threatened their entire philosophy. There's even this dramatic legend, probably not true, but it shows the feeling, about a student named Hippasus, who supposedly revealed this secret and got chucked overboard by his fellow Pythagoreans.
Wow. Drowned for discovering a number. That really shows how deeply it shook their foundations. It wasn't just math. It was their whole worldview.
It really was. And the sources point out that the invention of number types didn't stop there. Over time, we came up with negative numbers, zero, fractions, imaginary numbers, and even more exotic things like quaternions and John Conway's surreal numbers, which are supposedly so vast they contain everything else. Each step just expanded our mathematical toolkit.
That really drives home the point that numbers aren't just out there waiting. We kind of invented them, or at least the concepts as we needed them.
Precisely. And the sources use this fascinating example. The Pirahan tribe in the Amazon. Historically, their culture just didn't need numbers beyond maybe one or two or many, so they didn't develop abstract counting.
So the takeaway there is numbers aren't automatically part of being human. They're learned, cultural tools.
That's what the sources suggest with that example, yeah. It contrasts with our ancestors. The material mentions very early signs of math thinking, like the Ashango bone. It's over 20,000 years old, and some think the notches on it might show prime number patterns.
So even way back then, before writing, people were spotting patterns, thinking about quantity abstractly.
Yes. And that jump from thinking about 10 sheep to just the abstract idea of 10, that was huge. That abstract thinking, developing over thousands of years, eventually led to visualizing numbers, like on the number line we use today. That line finally got a solid definition with mathematicians like Dedekind in the 19th century, fitting in all those real numbers. Understanding that long journey helps us see why I, which doesn't fit on that line, were such a big mental leap.
Okay, that sets things up nicely. Speaking of history and abstraction, the sources talk about the power of 10. Why do we end up with 10 as our main base?
Well, the material makes a pretty strong case that the answer is literally at your fingertips. 10 fingers. Early counting was physical fingers, toes, maybe pebbles, tally marks. Simple, but really limited for anything complex.
Yeah, try counting a big herd of animals or tracking the moon with just tally marks. Gets messy fast.
Exactly. The big breakthrough, the sources emphasize this, was positional notation. This is a huge takeaway. The idea that the same symbol, like a 3-foot, could mean different things depending on where you put it.
Right, like in 316, the 3-foot means 300. But in 613, it just means 3.
And the crucial invention that made positional notation really work was 0. The sources stress that 0 wasn't just nothing, it was a placeholder. Think about it. How do you write 603, 603, and make it clear it's not 63, 63 without a 0? The Babylonians and Mayans figured this out independently, which is pretty amazing.
Okay, so base 10 probably comes from our fingers. But the sources suggest we could have picked a different base, maybe even a better one.
Yeah, they make a case for base 12, or decimal. The key idea here is divisibility. 12 divides evenly by 2, 3, 4, and 6. 10 only divides evenly by 2 and 5. So fractions, like a third or a quarter, are much simpler, much cleaner in base 12.
That makes sense. 1/3 in base 10 is 0.333, repeating forever. What is it in base 12?
It would just be 0.4. Nice and simple. And the sources have this really cool bit about how some cultures actually counted to 12 using one hand, using your thumb to point to the segments on your other 4 fingers. Each finger has 3 segments, right? So 4 fingers, 3 segments each. That's 12. Then you could use the other hand to keep track of the dozens, getting you up to 144, a gross.
That's brilliant. So why didn't base 12 catch on everywhere? Why are we stuck with 10?
And mostly inertia, it seems. Once societies built their trade, their measurements, their whole way of thinking around tens, switching just became too difficult, too disruptive. It's kind of a historical accident that stuck.
But base 12 echoes are still around, like the sources point out. Dozens, grosses, 12 inches in a foot, 12 hours on a clock face, 12 months.
Exactly. Those are remnants, reminders that our base 10 system was a choice. Maybe not the mathematically neatest one, but it's fundamental now. It shows how something as basic as counting is shaped by, well, our bodies and history.
Okay, so from the structure of numbers, let's shift to some specific magic numbers that seem woven into the fabric of reality, often linking geometry and nature, pi and phi.
Ah, yes, the celebrity constants. Let's start with pi. The sources define it simply. It's the ratio of any circle's circumference to its diameter. Always the same number, no matter how big or small the circle.
And it's that famous number, 3.14159, and so on. It goes on forever, never repeats. The sources really highlight how long humans have been chasing this number.
Oh yeah, for thousands of years. The sources mention the Egyptians had an estimate around 3.16 over 3,800 years ago. Babylonians were close with about 3.125. Then people like Archimedes got clever, using polygons inside and outside a circle to trap pi's value between limits.
And before computers, the sources mention these incredible feats of patience, like Ludolf van Sulen spending years calculating pi to 35 decimal places by hand.
It's almost unbelievable now, right? when computers can crunch out trillions of digits. But here's the thing the sources point out. Even with all those known digits, Pi's sequence looks completely random. No pattern, no repetition found. Utterly chaotic, it seems.
They mention this idea of a normal number, where any string of digits like 7777 or 12345 should eventually appear just as often as any other string of the same length. Pi looks normal, but we can't prove it is.
Another mystery. The sources also flag that pi is transcendental. That means it's not the solution to any polynomial equation with simple whole number coefficients. This is a big deal, proved in the 19th century. It finally showed that the ancient Greek challenge of squaring the circle, making a square with the exact same area as the circle using only a compass and straight edge, is impossible.
And the name pi only came about much later, popularized by Euler from the Greek for perimeter.
That's right. And yeah, we celebrate Pi Day, March 14th. The sources even mention people like Akira Haraguchi who've memorized insane numbers of digits, like 100,000.
But here's the bit that kind of blew my mind from the sources, putting all those trillions of digits into perspective.
Ah, the NASA fact.
Yeah. NASA apparently only needs about 15 digits of pi for navigating the solar system accurately, and maybe 40 digits to measure the entire observable universe down to the width of a hydrogen atom.
It's incredible, isn't it? So why calculate trillions more?
That's the question. The sources suggest it's partly just pure curiosity, pushing boundaries, and maybe hoping we'll find some hidden pattern or use eventually.
Exactly, a scientific exploration for its own sake, plus testing computer power.
Okay, so sticky with constants that pop up unexpectedly, let's talk about the golden ratio phi.
Right, another special number, roughly 1.618. The sources define it through this unique proportion. If you divide a line into two parts, the ratio of the whole line to the longer part is the same as the ratio of the longer part to the shorter part, often shown with the golden rectangle.
And this one has a long history of, like, reverence. The sources mention the ancient Greeks, Pythagoras again, it's linked to the pentagram.
Yeah, they seem to find it aesthetically pleasing. It shows up in art and architecture, like supposedly in the Parthenon. And later, artists like Da Vinci and Raphael were thought to have used it.
There's just something about that proportion that feels harmonious, balanced.
It's often associated with beauty, yeah. And the sources connect it directly to the Fibonacci sequence, 1, 1, 2, 3, 5, 8, and so on. If you take the ratio of consecutive Fibonacci numbers, like 85 or 138, it gets closer and closer to 5.
And this is where it gets really interesting, connecting to nature.
Absolutely. This is a key point in the sources. Phi appears in the arrangement of petals on many flowers, the spirals of seeds in a sunflower, the curves of nautilus shells, and even maybe in the human body. Proportions of bones, facial features, maybe where your belly button is relative to your height. Some sources even suggest links to heart rhythms or the structure of DNA.
But this leads to that big question the sources raise. Is this actual evidence of some underlying mathematical design in nature? Or are we just really good at finding patterns, maybe seeing phi where it's just natural variation?
It's an ongoing debate. Are we imposing the pattern? But the connection, whether intended or emergent, between this abstract number and the living world is undeniably fascinating. It's one of those core magic number ideas.
Okay, from numbers tie to shape and proportion, let's move to Euler's number, yeah. The sources say this one, about 2.71828, comes not from geometry, but from growth.
Exactly, and it's fundamentally about exponential growth. The sources trace its discovery partly back to Jacob Bernoulli in the late 1600s. He was looking at compound interest.
Ah, the money example. If you invest, say, $1 at 100% interest for a year, compounded once, you get $2. But if it's compounded twice,
you get a bit more, $2.25. Compounded quarterly, monthly, daily, you keep getting slightly more. Bernoulli asked, what happens if you compound it continuously, an infinite number of times? He found the amount doesn't shoot off to infinity, it approaches a limit. That limit is E. The formula looks like 1 plus 1n as n gets infinitely large.
So a key thing about E is that it wasn't defined by shapes or simple fractions, but as the result of a process, a limit.
Precisely. And he turned out to be incredibly fundamental because it describes how things grow or decay naturally all over the place. Radioactive decay, population growth, how things cool down or heat up.
And the sources mention some really surprising places E shows up, not just physics and biology.
Yeah, like improbability. If you randomly rearrange a bunch of items, the chance that none end up back in their original spot is roughly 1 divided by E. Or there's this classic decision problem, the secretary problem. If you're interviewing candidates one by one and have to decide immediately, the best strategy involves observing about the first 1n, roughly 37% of them, then picking the next one who's better than anyone you've seen so far.
That's wild.
Yeah.
There was also that weird thing about cutting a rope.
Oh, yeah. If you want to cut a rope into pieces so that the product of their lengths is as large as possible, the ideal length for each piece is E. Around 2.718, it just pops up everywhere. And in calculus, it has this beautiful property. The function e to the power of x is its own derivative. Its rate of change is itself.
Which leads us to maybe the most famous equation in math, Euler's identity.
E to the power of I times pi plus 1 equals 0, or EI plus 1 equals 0. The sources really emphasize the beauty here. It links 5 of the most fundamental constants in mathematics. E from growth, I the imaginary unit, pi from circles, 1 the basic unit, and 0 nothingness.
Wow. To bring together numbers from algebra, geometry, calculus, these totally different areas, into one simple perfect equation, it really does feel like it reveals some deep connection, some hidden harmony. It's often called the most beautiful equation for that reason. And Euler himself, Leonhard Euler, was just a giant. The sources list just a few things he did. Solved the Basel problem connecting squares and pi, figured out properties of shapes that don't change when you bend them, Euler characteristic, basically invented graph theory by solving the Königsberg Bridges puzzle.
And he did a lot of this after going blind. Incredible focus.
Truly amazing. The sources even had that nice personal touch, mentioning the author tracing their own academic family tree back to Euler through their professors. Shows his lasting impact.
Okay, from these special constants, let's dive into the building blocks themselves. The primes.
Prime numbers. Whole numbers bigger than 1, only divisible by 1 in themselves. 2, 3, 5, 7, 11, 13, and so on. Simple definition, as the sources say, but their behavior, anything but simple.
And the first huge discovery about them, from way back with Euclid in ancient Greece, is that there are infinitely many primes. They never stop.
Correct. We know they go on forever. Yet, finding them, predicting where the next one will be, it seems completely chaotic. There's no simple formula. The prime number theorem gives us an idea of how they thin out as numbers get bigger, but it's just an approximation, not a precise map.
And this randomness, this unpredictability, the sources stress this is absolutely vital for our modern world, for keeping information secure online.
It's maybe one of the most direct, impactful takeaways from all this material. Modern encryption, like the RSA system protecting your bank account, your email, secure websites, it relies heavily on the fact that it's really, really hard for computers to find the two large prime numbers that were multiplied together to make an even larger number.
So if I have a huge number, say 1,000 digits long, that I know is the product of two 500-digit prime numbers, finding those original two primes is incredibly difficult.
Extremely difficult for current computers, yes. If you could do that quickly, you could break the encryption. The security rests on the difficulty of factoring large numbers into their primes.
So the mystery of prime distribution is literally what's keeping things safe.
In a very real sense, yes. That's why things like the Riemann hypothesis are such a big deal. It's deeply connected to understanding prime distribution. If someone solved it and it led to a fast way to factor, well, that could cause a massive cybersecurity problem. There's $1 million prize for solving it, by the way.
Wow. It's amazing how abstract math connects to something so practical, and there are still so many basic questions about primes we don't know the answer to.
Oh, tons. The sources list some great ones. Goldbach's conjecture. Can every even number bigger than 2 be written as the sum of two primes? Like 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5, 10 is 3 plus 7, or 5 plus 5. Seems true. Tested for unbelievably large numbers, but
Yeah.
no proof it's always true.
And then the gaps between primes, like twin primes, pairs of primes that are only 2 apart, like 11 and 13 or 17 and 19. Are there infinitely many pairs like that?
Or cousin primes, gap of 4, sexy primes, gap of 6. We suspect there are infinitely many of all these, but again, no proof. Although the sources mention Tang Zhang's huge breakthrough in 2013, he proved there are infinitely many prime pairs with some finite gap less than 70 million. A massive step.
It feels like a frontier that's still being actively explored.
Definitely. People look for weird primes, too, like palindromic ones, read the same forwards and backwards, or primes related to Euclid's work. The sources even had that funny anecdote about the prime number norm in restaurants.
Oh yeah, serving things in prime quantities, like 5 shrimp instead of 4 or 6.
Exactly. The idea is it feels slightly awkward to divide evenly, maybe encouraging people to order more. A quirky psychological trick using primes.
That's brilliant. And the story about Dyson and Borel chatting in a cafe about weird prime patterns, it just shows this deep human fascination with these numbers.
It does. And that fascination fuels things like GIMP's The Great Internet Mersenne Prime Search. Thousands of people donate computer time to search for new, record-breakingly large primes, usually of a special form called Mersenne primes. There are even cash prizes for finding huge ones.
Okay, the world of primes is clearly rich with mystery, which leads perfectly into the next bit from the sources. These elegantly simple but cruelly unsolved problems.
Right. Problems you can explain easily, but that have stumped mathematicians for ages. The classic example the sources give is the Collatz conjecture, also called the 3n plus 1 problem.
Okay, the rule sounds simple enough. Pick any positive whole number. If it's even, cut it in half. If it's odd, multiply by 3 and add 1. Then just repeat with the result.
And the conjecture is just, does every starting number eventually hit 1, and then get stuck in that little 4-2-1 loop?
It feels like it should be easy to prove yes or no. Find one number that doesn't hit 1 or show they all must. But nope.
Nope. It's been tested for numbers up into the quintillions, maybe higher now. Every single one tested eventually lands on 1. But no one can prove it always will. No counterexample found. It's deceptively simple.
The sources call the sequences hailstone numbers because they can shoot way up before crashing down. Like starting with 27, it goes up over 9,000 before it finally comes back down to 1. But 26, right next to it, gets to 1 really quickly.
Exactly. That unpredictable jumping around makes it so hard to analyze. The sources say it brushes up against really deep areas like chaos theory, computability.
And it might even be undecidable, meaning maybe there just isn't a proof one way or the other using our current math. They quote Paul Erdens saying something like, "Mathematics is not yet ready for such problems."
It's a beautiful trap, as the sources put it. Looks invitingly simple, draws people in, but seems impenetrable. The key takeaway is just how hard it can be to prove something holds true for all infinite numbers, even if it works for the first billion you check.
It's interesting to contrast it with things like Euler's conjecture about sums of powers. That seemed plausible too, but eventually someone did find a counterexample.
Right. Lander and Parkin found that 27 euro plus 84 euros plus 110 mil plus 133 euro actually equals 140.44, just one counterexample, and the conjecture was dead. But for Collatz, that killer counterexample remains elusive. Maybe it doesn't exist. We just don't know.
Okay, another really old, unsolved problem from the sources. The search for odd perfect numbers.
Perfect numbers. The sources define these nicely. A number is perfect if you add up all its divisors, numbers that divide into it evenly, excluding the number itself, and the sum is equal to the number you started with. 6 is the classic. Its divisors are 1, 2, and 3, and 1 plus 2 plus 3 is 6.
And we know how to find even perfect numbers. Euclid found a formula linked to those Mersenne primes we talked about.
Exactly. If 2 to the power of p minus 1, 2p1 is a prime number, a Mersenne prime, then a specific formula involving that prime gives you an even perfect number. And Euler later proved that all even perfect numbers must come from this formula, so the even ones are understood.
But the big mystery, lingering for thousands of years, are there any odd perfect numbers?
It's one of the oldest unsolved questions in math. The sources stress this long history. Greeks, Arab mathematicians, Renaissance thinkers, modern computers, everyone's looked. And they've checked numbers up to absolutely staggering sizes, like 10 raised to the power of 2200. And nothing, not a single odd perfect number found.
Wow. And the sources mention that famous story about Frank Cole proving a supposedly prime number wasn't prime back in 1903.
Yeah, the number 267.1. It was thought to be prime, which would have generated a huge even perfect number. Cole went to a math meeting, silently did the enormous calculation on the blackboard to factor it, got the answer, then sat down. Apparently he got a standing ovation. It showed how hard verifying these things was back then. But back to odd perfects. The lack of finding one isn't for lack of trying. And here's a key nugget from the sources. Over time, mathematicians have proved a whole list of really specific properties that an odd perfect number must satisfy, if one exists.
Like what kind of properties?
Well, it would have to have at least 10 different prime factors. Its biggest prime factor would have to be enormous, over 100 million. It has to leave a remainder of 1 when divided by 12. It can't be divisible by 105, and the list goes on.
And the point is, each new restriction makes it seem less likely that such a number could actually exist, like threading an increasingly difficult needle.
Exactly. The conditions become very restrictive. People also study spoofs numbers that almost work but just fail one condition, hoping they give clues. There are arguments based on probability suggesting odd perfects probably don't exist, but that's not a proof. The question remains wide open.
Amazing that such an old question is still unanswered. Okay, finally, let's talk about an inspiring human story woven into this mathematical tapestry. Sophie Germain.
Yes, a truly remarkable figure. The sources tell her story well. She had this intense passion for math in late 18th, early 19th century France, but her parents actively tried to stop her. They thought it wasn't suitable for a young woman. They'd take away her candles, her heat.
But she studied anyway, right, in secret, wrapped in blankets.
She did. And because women just weren't accepted in academia then, she started writing to famous mathematicians like Lagrange using a man's name, Monsieur Leblanc. He was so impressed with the insights in his letters.
He wanted to meet this Monsieur Leblanc.
Exactly. And the sources say when he found out Leblanc was actually Sophie Germain, he was surprised, but became a huge supporter and mentor, which was crucial. She went on to make real contributions, even without a formal position for most of her life.
Including work related to Fermat's last theorem.
Yes, she did important work on a specific case of Fermat's last theorem, developing methods that were useful later. And she came up with the idea of Sophie Germain primes. That's a prime number, p, where if you calculate 2p plus 1, that also turns out to be prime, like 5 is prime, and 25 plus 1, which is also prime. So 5 is a Sophie Germain prime. And the sources note these primes turned out to be important later in number theory and even in modern cryptography for creating safe primes.
And is it known if there are infinitely many Sophie Germain primes?
Nope. That's another open question related to primes. It just goes to show.
So many mysteries left. But Germain's most recognized work was in a different field, elasticity.
Right. She tackled the physics problem of how surfaces vibrate, think like a drum skin or a metal plate. She developed a mathematical equation to describe these vibrations, explaining the beautiful patterns called Claudetni figures that sand makes on vibrating plates.
And she actually won a prize for that work from the French Academy of Sciences.
She did in 1816. The sources highlight she was the first woman ever to win their prize for mathematics. A huge achievement, overcoming incredible barriers. Her legacy touches both pure math and applied physics and engineering. Just an incredibly inspiring story of perseverance.
Wow. What a journey through the world of numbers, pulling all that from the sources you shared.
It really covers a lot of ground, doesn't it? From just sorting numbers into types, real, imaginary, rational, irrational, to how we write them with zero and place value. Then meeting the big constants like pi, phi, e that shape geometry and growth. Diving into the deep mysteries and practical importance of prime numbers. And wrestling with those problems like colats and odd perfects that seem so simple but remain unsolved. Plus, hearing about pioneers like Germain.
This whole deep dive makes it so clear. Numbers aren't just bookkeeping tools. They're filled with genuine mystery, unexpected connections. They're endlessly fascinating. It really does feel like a hidden language describing how the universe works.
And it connects back to you, the listener, in surprising ways. These abstract ideas, they influence the design of things around you, they describe natural processes, and yeah, they literally protect your digital identity every day through prime numbers.
It definitely makes you think. We saw how simple rules can lead to mind-boggling complexity, like colats, and fundamental questions like odd perfect numbers are still open after centuries. What other really basic truths might be hiding in the math of everyday life, just waiting for us to look closer?
And here's a final thought to chew on. Building on that idea about pi potentially being a normal number, if pi's digits really do contain every possible sequence of numbers, your phone number, your birthday, everything could have, the answer to the Collatz conjecture, or the properties of an odd perfect number, or maybe even deeper secrets about reality itself, being coded somewhere in that endless chaotic stream of digits, just waiting to be found.